Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's lesson, we'll be investigating how to show that a figure is a parallelogram. So let's get started with the following problem here. What are the values of x and y, respectively, such that the two quadrilaterals are parallelograms? Notice that the values for x and y will be different for part A than part B. So let's get started with part A. Well, we know that by the definition of parallelogram, the opposite sides are parallel. But let's review the properties here that we learned in the previous lesson. So we learned that number one, a diagonal of a parallelogram divides the parallelogram into two congruent triangles. Then secondly, we learned that opposite sides of a parallelogram are congruent. Thirdly, opposite angles of a parallelogram are congruent. Fourth, consecutive angles are supplementary. And number five, the diagonals of a parallelogram bisect each other. So in order to solve for part A, we can use one of the properties here. For example, to solve for y, we can use that opposite sides of a parallelogram are congruent. So how do we solve this then? Well, we can simply write that 4y plus 21 is equal to 7y. And now we just need to simply solve for y, correct? So what we can do here, for example, is subtract 4 on both sides. So we end up with 3y is equal to 21. And then once we divide by 3, we get a y value of equal to 7. And there you go, we have the value for y. How do we solve for the x value? Well, here we can use another property, right? First, we can state that by the definition of parallelograms, opposite sides are parallel. And let me denote that in the diagram here. So we know that this side is parallel to this side here. Okay. And now we can use the theorem pertaining to parallel lines. Basically, if two parallel lines are cut by transversal, then alternate interior angles are congruent. And now we know that these two angles here, 3x and 45 degrees, must be congruent. So now we can just simply write that 3x must be equal to 45, and we end up with a value of 15. And that is basically the x value here. Okay, so we did find the x and the y value for part A. What about part B? Well, for part B, we can simply state that by the definition of parallelogram, opposite sides are parallel, okay? So here I'm referring to these two sides over here that I'm circling, okay? So since these two sides are parallel, then what can we say about these two angles here? So let me highlight this angle and this angle. Well, we know that those are the same side interior angles and they must add up to 180 degrees. They're supplementary, okay? So basically what we want to write here is that 2x minus 5 plus 123, all of that should equal to 180, okay? And then once you're writing the equation, you want to solve for the value of x. So here I can use my math function and simply select solve for x, and there you go, we have an x value of 31 here, okay? Okay, so now we want to figure out the y value, okay? So again, we can use the other property in which opposite angles of a parallelogram are congruent. And it actually makes sense that they're congruent because if this angle here is supplementary to this angle here that I'm circling, and this angle is supplementary to this angle, then by the transitive property, these two angles over here must be congruent, okay? Okay, so let's write that all in. Okay, again, opposite angles are congruent. Therefore, we can write that 3y has to be equal to 123. And again, we want to solve for the value of y here. And let's see what we get. Okay, we get a y value of equal to 41. Okay, so that's how we solve for the x and y value. Now, in this problem, we had to show that this figure was a parallelogram using any of these properties. But the question is, are these properties always valid if you don't know that the shape is a parallelogram? So basically here we assumed that this is a parallelogram, right? We assumed it, and that's why we're able to use these properties. But again, the question is, if you don't know if it's a parallelogram or not, can you use the same property? Let me give you an example here. Let's take, for instance, the first property. A diagonal of a parallelogram divides the parallelogram into two congruent triangles. So since here we want to show that the figure is a parallelogram, let's convert that property into the following. So basically we're saying if the statement is true. If the diagonals of a quadrilateral divide the quadrilateral into two congruent triangles, then the quadrilateral is a parallelogram. And that's what we're trying to figure out. Is this true or not? And basically, we want to think about all the properties of the parallelogram if we can somehow use them to show that a quadrilateral or figure is a parallelogram. But let's think about this particular statement here. Is it always true or not? Well, obviously, if we draw some random quadrilateral here like this, so let's draw some random quadrilateral, then, if we, for example, let me get the ruler here. Let's say we are drawing this in like this, okay, the diagonal, okay. Then the question is it always true or not that these two are congruent? Well, the thing is that it cannot just be some random quadrilateral, okay? So, obviously, it would work if the quadrilateral is a parallelogram, but does it work for any quadrilateral? Okay, so here's an example. For example, if we take the kite, okay, so let me write kite over here. So again, for a kite, the property is that these two segments are congruent and these two segments here are congruent. But segment AB and BC are not necessarily congruent to each other, and so segment AD and DC are not congruent to each other. Basically, these two triangles are congruent this way, okay? But what if we drew another diagonal, okay? So let's say we're drawing another diagonal here. Let me get a line from B to D, okay, like that. Then the question is, are these two triangles congruent, okay? And the answer is no. So it turns out that this property actually is not true, okay? This is not the case. So in today's lesson, we want to figure out, okay, how do you show that a figure is a parallelogram? What are the conditions that must be satisfied? Well, we know that that property here is not possible. So if we go back here to all these properties here, we cannot simply use these properties here to show that a figure is a parallelogram. We must think of some other properties, okay? So let's think about those properties now. So let's say we have a quadrilateral here, as shown in the figure. Let's call this quadrilateral ABCD. What conditions must be satisfied such that the quadrilateral is a parallelogram? So let's think about this. Obviously, we cannot just simply say that the diagonals bisect the quadrilateral into two congruent triangles, because we know that simply is not true. It doesn't become a parallelogram. However, if we think about, for example, the following, let's make these two segments congruent, okay? So let's say we shift this like that, and let's say we somehow try to make it congruent, okay? And the other segments, let's make them congruent as well, like that. Well, what can we say now? Must it be true that ABCD has to be a parallelogram or not? Well, the answer is yes, because you cannot have a quadrilateral in which both pairs of opposite sides are congruent and then it becomes not a parallelogram. So that's not possible. So it has to be a parallelogram. So let's write this in. So the first property is that if both pairs of opposite sides of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Okay, so that's one of them. What else must be true? Well, let's think about the definition here, and specifically the definition of parallelograms, okay? So let's say that both sides of this quadrilateral, both opposite sides are parallel. Then what must be true here? So let's actually draw that in. So imagine that this here is parallel to this side. Okay, so let's do it the other way around. There you go. So that means that these two segments must be parallel. So let's make them look parallel here. And then we have these two pairs also are parallel, okay? So for example, in this case, let's fix it here such that it's parallel. Okay, it might look like a rectangle, but it's still okay because it turns out that a rectangle is indeed a parallelogram. If you move this around here like this, okay, so I don't want to hide the point here, but again, it doesn't matter how you move it. It turns out that if both pairs of opposite sides are parallel, then the quadrilateral must be a parallelogram. So let's write that in. Okay, so now that we have the second property, let's think about some other properties or conditions that must be satisfied here. Again, let's go back to our previous quadrilateral. Okay, so here we have our initial quadrilateral, and let's assume that these opposite sides here are parallel, okay? Not only parallel, but let's also make them congruent, okay? So let's put a crossbar here and here. So that means that these two segments must be parallel. So let's draw them parallel somehow. There you go. So now they look parallel. And not only that, but they must be also congruent. So they have to be equal in length, okay? So let's say they're like that. So they're parallel and congruent. Well, guess what? This has to be a parallelogram. You cannot have any other shapes here. So let's write that in as our third condition. Namely, if one pair of opposite sides of a quadrilateral are both congruent and parallel, then the quadrilateral is a parallelogram. Now let's think about a fourth condition here. Now, we basically pretty much discussed segments, either parallel or congruent. But what about angles, okay? So let's say that we make these two angles congruent, okay? Okay, so let's fix that a little bit, such that they kind of look congruent here. All right, let's say it's like that. Well, that's still not sufficient because these could be other lengths, okay, here. So you can have, for example, a kite, and it doesn't become a parallelogram. So what if we make these other two pairs of angles also congruent, okay, like that? Well, in this case, let's make it like that, okay? Okay, so as a matter of fact, it turns out that if both pairs of opposite angles are congruent, then the quadrilateral is also a parallelogram. So that's our fourth condition. So basically, the wording is if both pairs of opposite angles of a quadrilateral are congruent, then the quadrilateral is a parallelogram. Let's now examine one last condition, okay? Which pretty much includes diagonals, okay? So there's something that can be said about diagonals. A specific condition about diagonals must be met such that the quadrilateral is a parallelogram. And which condition is that? Let's think about it. Well, let's draw the diagonals, okay? So let's say we have a diagonal here, okay, from B to D and one from A to C, okay? So, you know, we cannot make them congruent because then it's either going to be a square or a rhombus, okay? We want to be a little bit more general with that. So, for example, if we make a parallelogram like that, okay, so let's try to make a parallelogram, okay? There's something to be said about the diagonals here, okay? As a matter of fact, if that's the point where they intersect, and let's call that point, let's call it point E, that's fine. So there's something that to be said about segment AE, okay, and EC, okay? It turns out that they're going to be congruent, those two segments. And similarly, if you look at these two segments, DE and EB, they're also congruent. So what that means that those diagonals bisect each other, okay? So let's write that in. Basically, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. So that's basically it. So these are all the 5 conditions that must be satisfied such that we can say that the quadrilateral is a parallelogram. Okay, so let's see how we can apply these conditions that we have just discussed in a proof. Let's say we're given a quadrilateral math. We also know that segment AH bisects segment MT at point Q. Then we know that angle TMA is congruent to angle MTH. How do we prove that math is a parallelogram? Well, let's get started setting up a statement reason table. First, we want to also write quadrilateral math, which is given, and there's really not much we can conclude from that first step. So let's see what we can conclude with the second given, that segment AH bisects segment MT at point Q. So from the diagram, we have AH bisecting MT, so that means that this segment is going to be congruent to this segment over here, okay? So first, we do need to state that Q is the midpoint because we want to use a definition of segment bisector. So let's state that as step number 3. Okay, so Q is the midpoint of segment AH. Well, that's a definition of a segment bisector. And then we state that segment MQ is congruent to segment QT because that is a definition of a midpoint. Then we can state the other given that angle TMA is congruent to angle MTH as shown in the diagram. And then we can ask ourselves, okay, what can we conclude from that step? Well, maybe we can use that given to prove that triangle TQH is congruent to triangle MQA somehow, right? Well, the good news is we can. As a matter of fact, we can prove that these two angles here are congruent, right? Because those are the vertical angles, and we know that all vertical angles are congruent. So let's actually write that in the statement reason table. Okay, so once we have written that in the statement reason table, we can now prove that the triangles are congruent. So we can say that triangle TQH is congruent to triangle MQA because of the ASA postulate. Okay, so usually when we prove triangles congruent, we can use corresponding parts of those two congruent triangles to prove anything else that is congruent. Now, if we want to use one of the conditions that we have introduced, we can, for example, use the fact that if the diagonals bisect each other in a quadrilateral, then the quadrilateral is a parallelogram. And as a matter of fact, we can do that. If we, for example, prove that these two segments are congruent, then we can say that math is a parallelogram. Well, why are they congruent? Because those are the corresponding parts of those two congruent triangles. So again, let's write that in the statement reason table. So segment HQ is congruent to segment QA because corresponding parts of congruent triangles are congruent. Okay, so if we look at step number 4 and 8, we can now clearly see that those diagonals bisect each other. But in order to do that, we do need to be careful with the definition. So if we think about the definition of a segment bisector, we're referring somehow to a midpoint, okay? So first we need to state now that Q is not just the midpoint of segment AH, but also Q is the midpoint of segment MT. And by the way, going back here, this actually is an arrow. That should be Q is the midpoint of MT. So let me change that really quick. Okay, so now we can write that point Q is the midpoint of segment AH. Well, that is the definition of a midpoint because, again, here we have congruent segments here, okay? And now we can write that segment MT bisects segment AH at Q because, again, that's the definition of a segment bisector. Now, if we look at step 2 and 10, what do we notice here? Well, we notice that a segment AH bisects segment MT at Q, but also segment MT bisects segment AH at Q. So they basically bisect each other, okay? So now we can state that math is a parallelogram because if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. And this is how we can use any of these conditions here that I listed previously to solve algebraic problems and complete proofs in geometry. Okay, so that's basically it for today's lesson. Again, thank you for watching and have a wonderful day.